Can you see?
Yes, ma'am.
Is the PPT visible? Okay. So let us, we were doing Laplace transformation review. So let us consider an exponential form. Suppose we have an exponential function like a e to the power minus alpha t, which is 0 for t less than 0, and it is positive for t greater than or equal to 0. A and alpha are constants. So if you apply the definition, you will get Laplace transform of a e to the power minus alpha t is equal to greater equal to 0, you get a simple pole at s equal to minus alpha, right? So this is a exponential function. Similarly, we can have an step function which is defined as a for t greater than 0 and it is 0 for t less than 0, right? A is constant, and if you apply the definition, the Laplace transform of unit step function is a upon s. So the step function whose height is a is unity is called unit step function. When a is equal to 1, then it is called unit step function. And step inputs represents constant position inputs to a position control system. These waveforms can be used to test the system's ability to track a constant position target, such as antenna tracking and a satellite in geostationary orbit, right? So you can note down these two, or you can um, drive it yourself. I'm giving you some time. So other types of Laplace transform common functions are pulse function, unit impulse, which is denoted by a by t naught, which is 0 for t less than 0 and for t less t naught less than t. So it is basically an impulse for duration t 0 to t naught, right? So by applying the definition, the Laplace transform of this function is given by a upon t naught s into 1 minus e to the power minus s t naught, right? This is a pulse function, and if we try to find out the impulse function, which is a limiting case of a pulse width, no? Pulse width, if you have very infinitesimally um, wide pulse, then it is called impulse function. So it is basically described by a function gt where limit t tending to 0 a upon t naught. So the limiting case is that the pulse has uh, zero width and infinite height, right? So it is described mathematically like this. So the impulse function is a special limiting case of a pulse function. Since the height of the impulse function is a upon t naught and the duration is t naught, the area under the impulse is equal to a, right? So as the duration t naught approaches 0, the height approaches infinity, as I have already told you, but the area remains same, equal to a. This is the special feature of a impulse function. So if you take the Laplace transform of pulse function, so we get the Laplace transform of impulse function as limiting case of t naught tending to 0 a upon t naught s into 1 minus e to the power minus s t 0. So if you take the limits, if you substitute the limit, you get a value of a. right? So Laplace transform of a impulse function is A, where the impulse function whose area is equal to unity is called the unit impulse function, or it is also called as Dirac delta function, which is usually denoted by this notation delta t. This is very, very important definition. So I want all of you to take down the notes. This is mostly commonly used functions which are used in control systems, input functions. These are some of the properties of Laplace transform, that it can be translated. So suppose a function ft is Laplace transformable such that Laplace transform of ft is denoted by fs, and alpha is a scalar positive constant, then Laplace transform of ft minus alpha is simply e to the power minus alpha s into fs. Okay. This equation states that the translation of time function of ft by alpha corresponds to multiplication of the transform fs by e to the power minus alpha s, right? Similarly, multiplication of ft by e to the power minus alpha t. Suppose ft is a Laplace transformable such that Laplace transform of ft is fs and alpha is a scalar, then Laplace transform of e to the power minus alpha t ft is fs plus alpha. Okay, so the multiplication of ft by e to the power minus alpha t has the effect of replacing s by s plus alpha in the Laplace transform fs. So the relationship given in this equation is useful in finding the Laplace transform of functions such as e to the power minus alpha t sine omega t, e to the power minus alpha t cos omega t. So Laplace transform of sine omega t, as we already know, that is given by omega upon s square plus omega square, and Laplace transform of cos omega t is s upon s square plus omega square. Okay, suppose we want to take the Laplace transform of e to the power minus alpha t sine omega t, then simply use this equation and find out the Laplace transform of e to the power minus alpha t sine omega t. That will be fs plus alpha. So replace s by s plus alpha. So you get omega upon s plus alpha square plus omega square. All right. Similarly, e to the power minus alpha t cos omega t is replace s with s plus alpha. So it becomes s plus alpha upon s plus alpha square plus omega square. All right. So please note down these important properties. I am giving you some time. So other properties of Laplace transforms are change of time scale. So you can also change the time scale. So if Laplace transform of ft upon alpha, Laplace transform of ft is fs, then Laplace transform of ft upon alpha is basically alpha into f of alpha s. The change of time scale is useful when it is applied directly to a different system having similar mathematical equations. For example, if ft is e to the power minus t, then find the Laplace transform of ft by 5. Okay. So replace t by 5. So the Laplace transform becomes e to the power minus 0.2 t, right? So this, by using this property, we can say that Laplace transform of ft is Laplace transform of f to the power minus t equal to fs equal to 1 upon s plus 1. Hence, Laplace transform of t by 5 is Laplace transform of e to the power minus 0.2 t. So 5 f5s becomes 5 upon 5s plus 1. All right. So in some cases, ft possesses an impulse function at t equal to 0. Okay, then the lower limit of Laplace integral must be specified as to whether it is 0 minus or 0 plus. since the Laplace transform of ft differ from these two lower limits. So Laplace plus of ft is basically integral 0 plus to infinity ft e to the power minus st dt, and Laplace minus of ft is integral 0 minus 0 minus to infinity ft e to the power minus st dt. Okay, so basically it becomes Laplace plus of ft plus integral Laplace integral of 0 minus to 0 plus ft e to the power minus st dt. So ft involves an impulse function at t equal to 0, then Laplace plus of ft is not equal to Laplace minus of ft, since integral of 0 minus to 0 plus ft is not equal to 0, right? So this is basically a comment on lower limit of Laplace integral. So you can take down the notes. Theorems are, suppose that ft is Laplace transformable such that Laplace transform of ft is fs, then Laplace transform of the time derivative of ft is d by dt of ft is sfs minus f0. F0 is the value of ft evaluated at t equal to 0. Similarly, we obtain the Laplace transform of second derivative. So it is Laplace transform of d2 by dt2 of ft is given by s square fs minus sfs sf0 minus f0, where f dot 0 is the value of d by dt of ft evaluated at t equal to 0. So if you go on doing this, the Laplace transform of nth derivative of ft is given by Laplace transform of dn by dtn ft is Sn fs minus Sn minus 1 f0 minus Sn minus 2 f dot 0 up to S fn minus 2 0 minus fn minus 1 0, where f0 f dot 0 fn minus 1 0 are the values of ft d by dt of ft d by dn minus 1 by dtn minus 1 of ft respectively, evaluated at t equal to 0. So if all the initial values of ft and its derivative are equal to 0, then the Laplace transform of nth time derivative of ft is reduced to Sn fs. Okay, so please note down the theorem.
Okay, turning off the heater.
Other useful theorems are real integration theorem and complex differentiation theorem. So Laplace transform of ft dt is fs by fs by s plus f minus 1 0 by s, where f minus 0 is basically integral of ft evaluated at t equal to 0. Okay. So similarly, Laplace transform of tft is minus d by ds of fs, and Laplace transform of t square ft is d2 by ds2 fs. Okay, so you can continue this process for Laplace transform of tn ft as minus 1 to the power n dn by dsn fs, where n varies from 1, 2, 3 up to any value. So note down these also. Next. So, next. So, Next usual theorem is convolution integral. This is again a very important integral theorem. The integral 0 to t f1 t minus tau f2 tau d tau is called convolution integral between functions f1 t and f2 t, and is denoted by f1 t star f2 t. So we have f1 t star f2 t is basically integral 0 to t f1 t minus tau f2 tau d tau, or you can also represent it with integral 0 to t f1 tau f2 t minus tau d tau. In that case, it will be called f2t star f1t. So if f1t and f2t are piecewise continuous and exponential order, then Laplace transform of f1t star f2t is given by Laplace transform of f1t star f2t is equal to Laplace transform of integral 0 to t f1 t minus tau f2 tau d tau equal to f1s f2s, where f1s is Laplace transform of f1t and f2s is Laplace transform of f2t. Excuse me. So this is convolution theorem. So you can note down this. Meanwhile, I'll take your attendance and create a class on Google Classroom.